ended with last time was the example of Z2 to the n. I just worked out the characters. I mean, it comes follows from characters of Z2. Z2 has only two characters, the trivial character and the one that there's only one other thing. So from there it comes, but the way it is indexed and all, it's better to get used to this notion. I'm hoping to do a little bit with this. Uh, yeah, so I did not give a full map of what I mean. So basically, although I will do a little bit of these generalities, almost all the applications, so to speak, of Fourier analysis that we are going to do will be with these four groups or four classes of groups: Zn, the and Z2 to the n, and integers, or rather, well, okay, so let's write integers, or so let's not write integers. Let me write the discrete, the torus, the multiplicative group, and R, and maybe RD, TD possibly. But so these are the four groups for which all the applications are going to come from these four things. So Z2 to the n is one of them. It's so just get used to this notation that the characters are indexed by subsets. Just yeah. So and that's how they are given. Okay. So chi s of x is x1, x2. I mean product of xi, I in s. These are the characters. But let me go back to the generalities. So we defined what we did last time was for any finite abelian group, we showed that the set of its character, it has if it has n elements, then it has n characters, and if you scale by square root n, they form an orthonormal basis for L2 of G. And additionally, we also got the I mean, we also defined the Fourier transform. Well, once it's an orthonormal basis, any function in L2 of G can be expanded in terms of the characters or scaled characters chi over square root n, and the coefficients are called the Fourier coefficients, f hat of chi. F hat of chi is just the inner product of f with chi over square root n, and that has this form. So this is pretty much what we did, and it works for all finite abelian groups. That was the point. Okay, so there are a couple of things I want to say here. One is to say one is the so the how did we do this? So one is we did it by showing I mean using the structure theorem for finite abelian groups. So Ritvik made a comment, so let me go to that now. So okay, so let's do a little bit here. So maybe I go to the next page itself. So let's do it here. So let's take G finite abelian group, and G hat is the set of its characters. So n is the size of G, which is also the size of G hat. Okay. Now, and if f is in L2 of G, okay. So rather before that, so and the other statement is that chi over root n is orthonormal basis for L2 of G. So here is another view of the characters. So here let's define these translation operators. So for any group element X, so I define an operator from L2 of the group to itself. Okay, so it's a linear transformation defined like this. How does it act on a function? So, well, we know how does it act on a function? It just translates the function by x. It's the same function sort of translated by x. So these are called translation operators. For every x in the group, we have one operator like this. So then, so what you can observe is that, so these are of course linear transformations. So what is the, but one observation is that if chi is a character, then what does the translation operator do to it? Okay, so it is by definition chi of x plus y, but since it's a character, it's a homomorphism, so it is chi x chi y. So what we see is that tx applied to chi gives us chi of x times chi. So that is chi is an eigenvector of tx with eigenvalue uh, which is chi of x. Okay, so chi is, so I can call it eigenfunction or eigenvector. I just called it eigenvector if you want to arrange it as a vector, but otherwise you can call it eigenfunction if you like, it doesn't matter. But it's an eigenvector of this tx and the eigenvalue is this chi of x, right? So you see that the same chi is eigenvector. So this is true for all x. So chi is a common chi in G hat is a common eigenvector. To all the translation operators simultaneously. So this is one property. So these characters are actually eigen vectors of this. But this is a bit strange. So what Ritwik suggested was to, you can use this in reverse. Okay, so let me change color and write it. So you can do this in reverse. So instead of, so you could use this. So here is an alternate approach. Approach to what? To saying that an finite abelian group has n characters and they form an orthonormal basis for L2 of G. So here, so what I did was started with Zn, then it works for products of cyclic groups, and every finite abelian group is a product of cyclic groups, hence done. But here is another approach which does not use the structure theorem. This is what Ritwik was suggesting. So let's start with this. Forget this observation. Okay. Forget this observation. You start here. So you look at all these operators Tx. So two things. One is Tx, Ty is actually Tx plus y. So it's also Ty Tx. So what does Tx, Ty do to a function? First you translate by y and then you translate by x. So all of these map f to f of whatever be the argument dot plus x plus y. Okay, so these are all, both all these are this. Okay, so this is point number one. Very easy because this is happening because it's an abelian group. Okay, otherwise Tx, Ty would not be Ty, Tx. Okay, so it is because it's abelian that otherwise you will get x, y, z and y, x, z. They are different things, but this is true. Second point is Tx adjoint is T minus x. Well, this is because, so this one I hope is clear. I didn't write out a justification, but you just work on any function, you just get Tx, Ty applied to f at z is f of z plus x plus y. That's all it is. Okay. Now Tx adjoint, what does that mean? Tx star f in our product G is supposed to be, well, or rather, yeah, Tx star fg is by definition f Txg, which is sum of f of z Txg of z conjugate over z. That's the inner product in L2 of G. But Tx G of, so this is f of z times G of x plus z conjugate summed over z, which you can just change variables and write x plus z as y. So this is f of y minus x G of y conjugate summed over y, but that is same as t minus xf, right? That is t minus, this is f translated by minus x, so it is t minus xf inner product with G. So Tx star is same as T minus X. Okay. So that is also there. So of course, as a consequence of these two, you see that Tx star, Tx is T minus X Tx, which is T0, which is 0 is the identity. I mean, so this will be the identity operator. So Tx are unitary. Okay. All that I have done here is that what we have, so we are not, so we have this, we just define these translation operators and we observe that that each of them is a unitary operator on L2 of G. Not only that, they commute with each other. So we have a commuting family of unitary operators. So whenever you have a commuting family of normal operators, everything here is on a finite dimensional space. Okay, so no need to worry. I may use say the word operator, but it means nothing. It's a matrix. Okay, so this is a commuting family of unitary matrices. So unitary matrices are normal. You know, normal means matrices which commute with the adjoint. So unitary matrices certainly commute with the adjoint. The product is identity. So what we see is that whenever you have a, so fact is from spectral theorem, or it's a slight extension of spectral theorem. I don't know if you would have seen this in basic linear algebra course or not, but it is a basic fact you should definitely know. So what this implies is that there is a, so this is, I will say, spectral theorem. It's a not for a single one. So spectral theorem basically says there is an orthonormal basis. Let's call them some collection. Okay, an orthonormal basis of L2 of G, each of whose elements is an eigenvector of all the Tx. So they can be simultaneously diagonalized. That is the phrase we use. When you have a commuting family of normal operators, they can be simultaneously diagonalized, which means that there is a common basis of eigenvectors, and that will be an orthonormal basis. So that will be, that's what we get. So now the point is, so let tau be such an eigenvector. That means Tx applied to tau is some eigenvalue. The eigenvalue depends on x. So the eigenvector is common, but the eigenvalues depend, right? So lambda x is the eigenvalue for some lambda x in complex numbers. In fact, mod lambda x has to be 1 because these are unitary operators. But so this is true, right? So for all x, we have some lambda x such that this happens. But then what is this lambda x? So if you look at tx tau, so this means you evaluate it at y. So tau of x plus y is equal to lambda x tau of y for all y in G. It's also true for all x in G. For each x, I apply this. So tau x tau applied at y is this tau at x plus y, and this right side is lambda x times tau at y. So now one point from here is that what this implies is that, see, tau is not 0. Tau, so from this we get that tau of y not equal to 0 for all y in the group, because see, if being an eigenvector, there is some coordinate which is not 0. There is some y for which tau of y is not 0, but then tau of x plus y is also not 0, right? So for every x. So you see that tau is never vanishing. So because of that, can normalize so that tau of 0 is 1. Eigenvectors are anyway okay up to constants, but I can't say tau of 0 can be normalized to 1 unless, but tau 0, if it is 0, then I cannot normalize it to 1. So I just made this small argument to say that tau 0 is not 0. Maybe you can give another argument, but anyway, so this tau 0 is not 0, so I can do this. But then what we see is that from here, tau of x, so tau of, so here put y equal to 0. You get tau of x is equal to lambda x. Set y equal to 0. This side is tau of x. This side is lambda x into tau of 0, which is now taken to be 1. So lambda x is nothing but tau x. So what this means is tau x plus y is tau of x times tau of y for all xy. That is, tau is a character. So here you came in the reverse direction. From the fact that you have commuting unitary operators, you get a orthonormal basis of eigenvectors. And what we show is that each of those eigenvectors, after normalizing so that they are one at identity, becomes a character. So you got a full basis of characters. So this is an alternate approach to saying that you have a full basis of characters. Okay, so anyway, you know both ways. So then you get yeah. So this is a point. So anyway, you should know both, that characters form eigenvectors, whether you take this as definition and come there, or whether you come from the other side and here, it's okay. But this is a okay. Any questions here so far? Okay. So this is characters as eigenvectors of the translation operators. So one of the corollary, question? Yeah.
No, just that statement that characters are eigenvectors. Is that a property of abelian groups? Is that the sort of general setting?
Well, what is a character? Right. So what should I say? So in general, characters are not homomorphisms. Characters are traces of representations. I mean, they are traces of homomorphisms into higher dimensional unitary groups. Do they form eigenvectors of the? No, I mean they don't. So well, there is no common eigenvectors first of all in general. So they don't commute. These translation operators do not commute. There is some related point, but it is not exactly this. I mean, the translation operators do not commute.
Okay, thanks.
Yeah. So okay. So yeah. So yeah, let me stay with abelian. Okay, I maybe, so somebody knows something which, I mean, see, I'm not expert in any of these topics. As I said, some of you may actually know some of these things. So you are most welcome to also interrupt and correct me if I say something.
The reason I asked the question is actually like I have been trying to study structure of eigenvectors, and to me this is an interesting property of an eigenvector, meaning like leave alone the other context. So I'm trying to see in what contexts eigenvectors have such beautiful structure. That's all. Thanks.
Well, it is very special actually. So these are, I mean, yeah. So these are coming from a group structure actually. So this is, I mean, so there is something to do with eigenvectors and characters in non-abelian setting, but it's not this straightforward. I mean, it's a bit more. Yeah, I don't even remember exactly. Okay, so maybe we can see that later. Yeah.
Some other time later. Yeah, thank you.
Yeah. Okay, so one, yeah. Any other questions, comments? Okay, so yeah, what do I want to say now? Yeah, what did I want to say? Okay, so we want to study, yeah, so we have now this full basis of eigenvectors. We want to study the basic properties of this Fourier transform. Okay, so last time I said one thing, so namely the Plancherel theorem. The Fourier transform is a unitary operator from L2 of G to L2 of G hat. So that means this. This is one of the basic properties. But I want to see more. Okay, so but yeah, what is it I want to? So there was a small point I wanted to say. For those of you who are more used to probability language, I mean, everyone should be used to this basic probability language, nothing complicated. So here is a small interpretation. So for f in L2 of G, you remember, and chi in G hat, remember f hat of chi by definition is 1 by square root n inner product of f with chi. Okay, so these are the Fourier coefficients. Okay. So two things. One is the trivial character, where every group element is mapped to 1. Okay, every group element is mapped to 1. That is the trivial character. And so what is f hat of that character? It is 1 by square root n. Inner product of f with 1 is just f of x in the group. Okay. Also, second point, so this is point number 1. Point number 2 is we know the Plancherel relation tells you that if I add the sum of squares of the characters, I mean absolute squares, these are in general complex numbers, it's the same as summing f of x square, absolute value square, over the group elements. Okay. Two things from here. So what you see is that if you think of, if you want a probabilistic meaning, so consider let P be the uniform probability on the group. That is, you put probability mass of any element to be 1 by n. You pick an element in the group at random. That's how we say in probability. So you consider a probability measure which puts 1 by n mass at each of the points. Then, so f is now a random variable here. So the expected value of f with respect to p, everything with respect to p, expected value of f is of course 1 by n. It's the average value of the function. So which is in fact, actually, if you see this, it is in fact 1 by square root n times f hat of 1. So f hat of 1 has this meaning that it is related to the expected value of the function. It's not the average value. The way I normalize this by root n, therefore it is not the expected value, but it is square root n times the expected value. Also, what is the variance? Variance of the function is the expected value of the square, so is 1 by n. By definition, the variance is square minus the expected value square. Okay, so the square of the, I mean, mean of the squares minus square of the mean. That's what the variance is. And in this case, what does it turn out to be? We know by Plancherel relation that the first one is just 1 over n, sum over all the characters of f hat of chi squared. And already we know that 1 by, what is 1 by n summation f of x? Uh, that is 1 by square root n f hat of 1. So if you square it, you get it is 1 by n f hat of the trivial character squared. So what happens? You just subtracting one term. So what you get is 1 by n sum over all the non-trivial characters of f hat of chi squared. Okay. So this is if you like, you can take this probability interpretation that the f hat of the trivial character is related to the mean, and the sum of squares of the remaining Fourier coefficients is related to the variance. Okay, in this way. So I just wanted to say that if you are not too happy with probability language, you don't have to do this. Okay. Anyway, so let me proceed. So what I want to study is basic properties of the Fourier transform on a general finite abelian group. One thing we have already seen, namely the Plancherel relation. This is one of the important ones. But on Z mod n, when I started with the example of Z mod n, which is the simplest case. In fact, one of the cases we care about. We are not too interested in the very general case, but anyway, it is worth knowing. So here we had, oops, what happened? Sorry. Yeah, so we had Plancherel relation was one. Then I had this Fourier inversion formula also. So now I want to talk about Fourier inversion. What was Fourier inversion formula? If you see there in Z mod n, the group elements were 0, 1 up to n minus 1, right? And the characters were these chi sub k e to the 2 pi I j k over n. Okay, so you could kind of identify that also as 0, 1 to up to n minus 1. We call them chi 0, chi 1 up to chi n minus 1. And in fact, we were not writing f hat of chi, but f hat of k. So it looked like f and f hat were both functions on the same thing, 0, 1 up to n minus 1. And what Fourier inversion said was basically that the way you go from f to f hat and the way you go from f hat to f is more or less the same, up to a small sign change, which is why I introduced this check notation. But that is already looking confusing in the general situation. Okay, is it because the f is a function on g and f hat is a function on g hat? Now g and g hat have the same size, but what is the relationship? I mean, it's not clear. So that's what I want to talk about next. So the duality. Okay, so let's talk about. So I want to get to Fourier inversion, but first I have to understand what is G hat. So G is now a finite abelian group. And N is the cardinality of G, and G hat is the set of characters. So far it is just a set. Okay, there was no structure. So now we put a group structure on G hat. What is a group structure on G hat? G hat consists of functions, right? So just pointwise multiplication. Okay, that's my this. So if chi1 and chi2 belong to G hat, what I mean by chi1, chi2, you can put a dot, or not put a dot, but chi1, chi2 is the function which takes x to chi1x, chi2x. Is that a character? It's clearly a character, right? Because if you put x plus y, you will get chi1 of x plus y, chi2 of x plus y. Both of them factor as chi1x, chi1y, chi2x, chi2y. And that gives you chi1, chi2 of x times. So it's clearly a character. that it's a homomorphism, product of two homomorphisms, everything is abelian. So it's actually clear that that is also a homomorphism into the circle group. It's all into the circle group because product of two elements in the unit circle is in the unit circle. Also, chi inverse of x, by that I mean chi of x inverse in the circle group, which is same as chi of x conjugate, because on the circle inverting is same as conjugation. This is also a character. It's clear. I mean, if you take x plus y, you will get chi of x plus y inverse, which is chi x chi y inverse. So it's the product of chi x inverse and chi y inverse. So this is character. So and the identity is of course the trivial character. The trivial character which maps everything to one. That's so this is a group. So G hat is a finite abelian group also. So earlier I had G hat only as a set. Now I am saying more. G hat is actually, if you put a multiplication operation, pointwise multiplication of functions, then it becomes a finite abelian group. Okay, so the example was, I mean, so one example is, I mean, okay, well, all are examples, so let's not bother. But is it isomorphic to G? So let's ask that question. Is G hat as a group isomorphic to G or not? Okay, what do you say? Would you say it's isomorphic? So you can go back to the structure theorem. Okay, so for Zn it is true. For Zn, Zn Zn hat is chi 0, chi 1, chi n minus 1. Let's remember what is chi sub k. Chi sub k of j is e to the 2 pi I k j over n. So what is pointwise multiplication? Chi k chi l of j is going to be e to the 2 pi I k plus l into j over n. But that is same as, see, if k plus l is more than n, it is same as e to the 2 pi I j over n into, I can write k plus l mod n. Okay, if it is n plus something, that n you can cancel and e to the 2 pi I j will be 1, right? So it is same as this. So it is same as chi k plus l mod n. That's what I mean. So it's clear that k going to chi k is an isomorphism. That's what I mean. Here the addition is modulo n and chi k chi l is exactly chi k plus l mod n. So it is this is an isomorphism, right? So it's clear that this is an isomorphism. What if I have a general abelian group like Zn1 plus Zn, say p. So I have some n1, n2, np. What will be its, what is G hat? Do you remember? So what is the G hat? How do you get G hat of this? Well, it's actually you take a character here, and so on. So you can take k1 up to kp, and the what do you map it to? Chi k1 tensor, chi k2 tensor, chi kp. This is an isomorphism. So it is true that the answer is yes. Okay, so is this clear? I mean, so since every finite abelian group is a product of cyclic groups, it is true. But I say that don't take it seriously. But don't take this seriously. Why? I mean, why not? I mean, so the thing is, this is not a natural isomorphism. Canonical or natural isomorphism between G and G hat. Okay, why not? In fact, it looks like I contradict myself because I just now produced natural isomorphisms, right? K going to chi sub k is a natural isomorphism, and K1 to Kp is a natural isomorphism. So why do I say there is no natural isomorphism between G and G hat? So what I want to say is this is not the duality is not this. I mean, so I will come to duality, but G hat is true that as group it is isomorphic to G, but it's not something to be taken too seriously because there is the isomorphism is not canonical. Okay, is that clear? What I mean by that to everyone when I say isomorphism is not canonical?
Not exactly. Do you mean there are multiple choices you can make for this?
Sorry.
I mean, why would you say it's not canonical? What would
Yeah.
count as
So yeah. So isomorphism means, I mean, see, isomorphism means just a relabeling, right? So I mean, so for example, Z3, somebody may write Z3 as 0, 1, and 2 with addition modulo 3, right? Someone else may write it as 1 omega and omega square. Someone else may write A, B, C with and give the group table. Now, is there, so all these are the same thing, of course. So this is just a relabeling. But is the isomorphism canonical? I mean, here it's not necessarily. I mean, so okay, at least sometimes there is a unique, unless you say what is the mapping. Okay, so well, I mean, I don't know if there is any mathematical definition. What I mean by natural isomorphism means everyone will choose the same, more or less. Okay, so if you take 0, 1, 2 and 1 omega omega square, well, it's not necessary that everyone will choose the same. So everyone will send 0 to 1, you have to, but someone may map 1 to omega and 2 to omega square, but it's also possible to map 1 to omega square and 2 to omega. That's perfectly reasonable. Okay,
right? So
and
there's
that's
some
also
arbitrariness in the choice that you make of the isomorphism. It's not really anything.
yeah. So that's why I say that G and G, but why I am asking, but I produce canonical isomorphisms, it looks like. Why do I say there is no canonical isomorphism? Yeah.
So the product structure is I mean, how you decompose it as product is where choice is involved, right?
Yes, exactly. So yeah, exactly. So the way you choose the product structure is not canonical. So there can be many ways. So you are given a group. So if you are given a group, I mean, so for example, so you take G to be this Klein 4 group. So which I'll write as 1 ABC with A square equals B square equals C square equals 1 and ABC, BC is A and CASB. So so you can write, this is actually isomorphic to Z2 cos Z2. But in what way? I mean, you can write it as 1A cos 1B. I mean, sort of, you can write it like that, or you can write it as 1B cos 1C also, etc. So the group itself is not, I mean, the structure theorem, there's no one obvious way in which to write it as a product. So each of these will give rise to, so the way you write G as Z2 cross Z2 will be different for different people, and that will lead to different isomorphisms with G hat. So it's not a canonical isomorphism. Okay. So we de-emphasize. This is exactly like with vector spaces. You know, if you have a finite dimensional vector space, the dual vector space is also a vector space of the same dimension. So obviously they are isomorphic, but there is no natural isomorphism between a vector space and its dual. But there is a natural isomorphism between a vector space and its double dual. That's exactly what is going to happen here. G hat is not isomorphic to G in a natural way, but G hat hat is going to be isomorphic to G. Okay, so that's where the duality comes.
So I realize that it's not important, but this can be made precise using category theory language, right? This non-naturalness.
Okay. Sorry. Who is asking?
This is Abhishek.
Yeah. Possibly, but I don't know any category language.
Okay.
Yeah. I mean, I believe you, but I don't know categories at all. So. Yeah. So G hat hat. I mean, so but okay. So that part, no, you're probably right. So, but that's can be formalized. But what is important to us is that there is actually a canonical isomorphism between G double hat and G. So how is that? Okay. So now that we have G hat is a group. So we can talk about G double hat. Okay. So now, but so G double hat is the set of characters on G hat, and we know that there will be n of them. We already know that G and G, this is a finite abelian group, so that also will be like that. But here is a thing. So for I want to say G double hat is same as G. So how is that? So you take an X in G and define the evaluation map from G hat to the torus by evaluation at chi, evaluation X at chi will be just chi of X. So it's exactly evaluation at X, that is the mapping. Okay, so then evaluation X is a homomorphism. So let me just write it belongs to G double hat. Why is that? I mean, so what I'm saying is EVX of chi1 chi2 is EVX of chi1 EVX of chi2, which is indeed true. This is chi1 chi2 at X, which is chi1 of X times chi2 of X by definition. So this is true. So every X in G gives you a element of G hat. So we have this map now from G to G hat, G double hat, which takes X to the evaluation map in G double hat. I mean, so this is an evaluation on, so this is in fact a nice, this is actually, okay, firstly, this is not only is this, yeah, so this, yeah, each EVX is here, but also evaluation of X plus Y is evaluation X plus evaluation Y. Okay, so that is also clear. So because evaluation X plus Y at chi is chi X plus Y is, sorry, what did I write here? Should I have written is chi X into chi Y? Sorry, I should write, yeah. Yeah, actually I'm using not additive notation this side, but okay, so this is actually, this is a homomorphism. And you can easily check that it is injective, so it is in fact an isomorphism. see, nothing can map to, so you take any x, it can't map to the trivial element in G double hat, because, so why is that not, yeah, so why is it injective? Okay, once you have that, it is injective. It's a homomorphism G from G to G double hat, and if it's injective, then it's an isomorphism because they are groups of the same size. So why is it injective? So it's injective because if you take, I mean, so evaluation x can't be trivial. So if EVX of chi is 1 for all chi, then, so that means EVX is trivial, means EVX of chi is 1 for all chi. That means chi of x is 1 for all chi. Now the characters form a basis for L2 of G. So they should separate points. See, we know that chi of 1 is 1 for, chi of 0 is 1 for all chi. If chi of x is 1 for all chi, then how can these characters separate 0 and x? So they can't form a basis, right? So if you take a function which takes different values and 0 at x, you can't produce it as a linear combination of characters. So this injectivity follows from there. So this gives a natural homomorphism between G and G double hat. Okay, so this is the duality. Any questions about this so far? So whatever, so all I'm saying is that once I have G, we could put a product structure on G hat, make it a group, then G double hat will be another group, but you don't keep getting a tower of groups. You will just, the next one will be the same as G. So G hat, and then G double hat is actually same as G. Even G hat is isomorphic to the same, but not in a canonical way. Okay. So now we can talk about Fourier inversion and such things. Okay, so now because we can identify G double hat with G, so now we have G hat, G double hat, which is same as G. I'll write equal to G. So I start with F in L2 of G and F hat in L2 of G hat. Then I can take the hat of that and I get F double hat in L2 of G double hat, which is same as L2 of G. So what is this F double hat? That's what I would like to know. Okay. I mean, I don't know if I lost people. Is it clear? If some details are not clear, you can easily fill them up. So if you did not get things like, okay, why was it injective or some specific thing, these are, nothing is here is actually profound. So it's all easy to check that this evaluation is a homomorphism. It's an isomorphism between G and G double hat. So just take it for granted. So now we have this G hat and G double hat, which is same as G. And I start with a function here, take its Fourier transform, which is a function back on the original group because I can identify G double hat with G. So what is this function is what I would like to know. Okay. So let's just remember the definition. F hat of, let's start here itself. What is F double dash of X? By definition, I mean it is at EVX, right? It is same as F double dash at EVX because X and EVX are, EVX is the element of G double hat that's identified with X. So, but what is that? It is the inner product of F hat with this character EVX in L2 of G hat, but I should divide by square root of n. Agree? That's the definition. The Fourier transform is by definition, you take F hat, which is the function whose Fourier transform we are taking. We are taking from a function here, namely F hat, its Fourier transform. So it's F hat inner product with the character, namely the evaluation, divided by square root n. But what is this? What is F hat evaluated? So this is 1 by square root n, sum of F hat of chi. So we are taking inner product in G hat, so chi in G hat, F hat of chi and evaluation x at chi conjugate, which is nothing but f hat of chi and chi of x, but conjugated. Right? That is right, yeah. So that is chi of x, but it's also chi of x conjugate is chi of minus x. So I can also write it as 1 by square root n f hat of chi of minus x. What is this? So if you remember the Fourier coefficients, why was f hat defined like that? You start with f. So we were writing f of x as sum of f hat of chi of x in g, but divided by square root n, and then f hat of chi was f inner product chi over square root n. Right? That was how we came to the Fourier transform, by expanding in chi over square root n. So if you look at this formula and compare with this, what is this actually? This is nothing but f of minus x, right? Did someone say something? So this is exactly, if you look at this formula, f at minus x. So what we are saying is f double hat is almost same as f, except it is flipped over. Okay, f double hat of x is f of minus x, that's all. So in other words, taking Fourier transform twice gives almost the same thing. So more precisely, I can say one of two things. If I take Fourier transform 4 times, I get back the function, because if I do it twice, I get back f negated in the argument. If I do it 2 more times, I'll get back f. Other option is you define the check. How is check defined? For f in L2 of g, f check of chi is defined as what is it defined as? 1 by square root n f inner product, I think chi bar. Okay, so if you define f check like this, then
times chi, right?
huh?
Chi bar times chi. I mean,
So f hat of chi was f inner product chi. So I think f check of chi is f inner product chi bar. I think.
okay.
Okay. It's inner product. So in other words, it is 1 by root n f of x chi of x. The conjugate, double conjugate goes away. So instead of like here, it was f of x chi bar of x, it is f of x chi of x. So then the claim is this, you take f hat and then take the check, you get back f. So your f hat is not exactly f, but f hat check is f. Or f check hat is also f, I suppose. Yeah. So this is the Fourier inversion formula for you. So in other words, the way to come back, so see f to f hat is a unitary transformation. You can always go back from f hat to f, that we know. But the way to go back from f hat to f is more or less the same as Fourier transform, meaning it's the check operation, not exactly hat, but the check, which looks more or less the same. So this is called Fourier inversion formula. Okay. Yeah, so that is one of the things that we do. Okay, so this is the duality. relation and the Fourier inversion formula. Okay, what else did I want to do? Okay, I'm nearly close to end, so I don't want to start a new thing, but let me just see in my notes if I want to say something specific here.
So
Yes.
the summations on the right should be over G hat, right? Not J. No, like up.
No, it is over G. Sorry, this is.
No. Not here. Above.
Oh, here. Yeah. Sorry, my chi and x kind of slowly homotopically changed from one to another. But yes, so all these are. Well, it's also chi in G hat. Yes, thanks. That is chi in G hat. Right. So one of the small corollaries of duality, I mean, as a small observation, since I am nearly out of time, so I will end with maybe this observation and let people ask questions. So if you take G, so as usual, G is a finite abelian group. If chi1 and chi2 are two characters, oh sorry. So we know that two characters are going to be orthogonal if they are distinct. But now let chi be a character, then if I sum chi of x, chi of y bar, okay, over all chi in G hat. Okay, I don't know why I got chi in G hat. Actually, I'm summing over chi. Actually, I'm fixing x and y. Fix 2 points in the group and sum over all there. So I say that you will get n if x equal to y and 0.
It's 1 o'clock.
If x not equal to y. Okay, because when x equal to y, it's clear this absolute value of 1 becomes 1 and n times you get n. But when x is, so this is different from the other orthogonality relation I had written was for two characters, but evaluated at the, I mean, so we take chi1 of x, chi2 of x bar and sum over x in G. And that gives n and 0 if chi1 not equal to chi2 and if chi1 equal to chi2. So this is slightly different and you can immediately see from duality why this is true. I will leave it to you. Okay, I will stop here. That's an exercise if you. Okay, so I will stop here and if there are any questions, I'll be happy to take.